And today, the first speaker is Martin Bies from UPenn, and he'll talk about root bundles and towards exact matter spectra of F-theory MSSMs. Thank you.
Thank you very much indeed for having me today. It's a great pleasure to speak again in the String Pheno Summer Series. It's actually great that you continue doing this, so that's perfect. So it's a great pleasure today to present work that has been done in collaboration with Miriam Swedic, Rondo Nagy, Miang Liu, and Marielle On. All of this circulates around establishing MSSMs in F-theory eventually. As we all know, standard model constructions in string theory have been almost omnipresent essentially since the early works of Candelas, Horowitz, Strominger, and Witten. Many of these works focus on the chiral spectrum, which means they establish exactly 3 chiral families. Once you increase the stakes a little bit and you go into actually establishing the correct vector-like spectra, then things become a lot harder. Still, vector-like spectra are an interesting thing to study, as these encode your Higgs fields, and these, as we know, literally matter. From a more conceptual point of view, you could say these vector-like spectra give you more insights into characteristic features of your QFT. So for these reasons, people have indeed studied also vector-like spectra in standard model constructions. And to my knowledge, the only one that managed to establish an MSSM construction in perturbative string theory is the work of Bouchard and Donaghy in 2005. Now, what we are doing here is we are trying to extend this to F-theory. F-theory, as we know, gives us a window into a non-perturbative regime of string theory, thereby, again, raising the question, can we find also MSSM constructions there? Or let's say, if you're more geometrically inspired, you could say there's this very beautiful interplay between geometry and physics in F-theory, so that it becomes a geometric challenge to establish this. And the current state of the affairs is that we have no MSSM construction in F-theory. What I'm reporting on today is technical advances that hopefully bring us closer to establishing this goal. Namely, we have been recently focusing on a very large class of very interesting F-theory standard model constructions, the so-called quadrillion standard models. And what has been known for quite some time now is that in these F-theory constructions, the vector-like spectra are counted by cohomologies of certain line bundles. What we have now uncovered here is that we don't just look at some line bundles, but actually at a very special class of line bundles, so-called root bundles. So the technical advances that I will be reporting on today are focused on these root bundles, telling you essentially what are root bundles, what can we learn about them, how can we make use of them in physics applications, and how far does it take us. So with that said, I'll start with a little bit of revision, namely how do we actually count vector-like spectra in F-theory. So I'm focusing here on 4D n equals 1 F-theory compactifications, which means you're starting with a singular full-fold. Codimension 1 loci, over which the fiber becomes singular, are the location of 7 branes. Codimension 2 loci in the base, over which the fiber becomes even more singular, are curves. These curves are where matter localizes, hence we call these matter curves. And of course, the matter comes as a certain representation. This representation we encode in a certain linear combination of P1s that we fiber over this curve. This fibration gives us what we call a matter surface and encodes the matter most compactly. Now, disclaimer is once you have your G4 and your matter surface fixed, there's a bit of machinery which you plug this data in, and out comes line bundle for you. I'll revise that in a moment. The upshot is a line bundle is more or less just telling you on a curve that you have a certain number of points marked, and you give an integer to these. And these numbers essentially tell you that you're looking for functions that vanish in these points to a certain order or have a pole in these points to a certain order. The number of these functions, or let's say that the set of these functions, is a vector space of finite dimension. This is what one calls a zeroth cohomology class of this line bundle. And these fields have an interpretation in the physics setting. These are massless chiral supermultiplets in representation R. And mathematically, there's also a first cohomology class for a line bundle, which corresponds to the H0 of the Zara dual bundle, which relates in essentially charge conjugation, so that we interpret the H1s as the massless chiral supermultiplets in the conjugate representation. The simple thing is the difference of these two dimensions of vector spaces, so H0 minus H1, that is the chiral index as a topological quantity. That is typically easy to determine. but finding the H0 and the H1 individually is typically hard because it's non-topological. So with that said, let me zoom in to the machinery a little bit further, namely tell you how actually this G4 and matter surface give you the line bundle in question. So the idea is to look at this commutative diagram that I have here. You would start with a G4 flux, which is in the bottom right element, the H22Z. From a math perspective, you would say this thing you want to lift somehow as a field strength. You want to somehow lift that to a gauge field, and the mathematical natural counterpart for gauge fields of such two integral forms are living in the linear cohomology. So this is well-established mathematics and also has been seen in the physics for quite a while. So the maps he had is surjective, which means any gauge field, gauge flux G4 that you're starting with, you can associate a gauge field A to. And now for technical simplifications, let me assume that I can even take it back via this gamma hat, which takes me to the Chow group. I should say this gamma hat is more or less surjective if and only if the Hodge conjecture is true, which is something that I'm of course not going to report on today or make any comments about. I'm just assuming that I can actually start with something in Chow too. And now Chow rings are done for intersection theory. This is an algebraic 2 cycle that you have here for your gauge field. The matter surface, being a surface, is also an algebraic 2 cycle, both of which are sitting in a fourfold. So you're intersecting an algebraic 2 cycle with an algebraic 2 cycle. Dimensions being complementary, move them in general position. You expect them to intersect in points, and you mark each point with a number, which is the intersection number in that point. Push that collection of points down, and you get exactly on the curve the line bundle, the prescription that I just gave before. Of course, you add the spin contribution to that, and that resulting line bundle is then the one that counts your fields. So with that said, that is essentially a revision of standard material. What happens if I apply this in the QSMs? So the QSMs are a class of geometries coming each with a choice of G4. So let us revise both of these in turns. So the geometries are a class of toric geometries that are obtained from triangulations of certain polytopes, subject to various physics constraints. Namely, we don't want chiral exotics, masses, we want gauge bosons, we want to constantly treat tadpole. And the authors, Svedich, Halverson, Lin, Liu, and Tian worked that out carefully for us and found that it actually boils down eventually to a constraint on the triple intersection number of the anti-canonical class of base B3. Namely, it requires that this thing is somewhat, well, having a choice of discrete values, it must be that this number, this triple intersection number, is either 6, 10, 18, or 30. That's the outcome. Now, as for the G4 flux, I'm also sketching the form of the G4 flux that we are seeing in these models. There's exactly this expression here. It's an algebraic 2 cycle. I'm writing here a G4 flux candidate, by which I mean that, of course, if we want to check that this thing is integral, we have to integrate over all 2 cycles and check there's an integer value for this integral. This is typically something that we can only do for a subset of all 2 cycles. This is the necessary conditions that were indeed checked in this work. So I'll proceed now under the assumption that this is indeed an H22 algebraic, which means, again, I know from the mathematics that there is gauge fields in the Chow group. And I could try to write down something very naive by saying, well, let me take this 3 factor minus 3 over k bar cubed times 5. And instead of having this one form E1 and this one form E4, I'll use the corresponding algebraic cycles, which in the case at hand turns out I'm looking for the vanishing of E1 and E4. Now, this thing is not in Chow with integer coefficients, and the reason for that is that Chow with integer coefficients means algebraic cycles, and I expand them with integers. But minus 3 times 5 over k bar cubed is not an integer, because k bar cubed is, by this previous result, 6, 10, 18, or 30. So that doesn't work. It's simply too naive. And essentially what I'm missing here is that actually, there's this intermediate Jacobian that also enters in the game here, and that has torsion elements. And to really properly lift this thing, that is the knowledge that I would require to write down these lifts. So they exist, but I'm simply not having the information necessary to write them down. So instead of looking into that in much detail, I try to circumvent this ignorance as it stands, and I look instead of at G4, I look at something which I would consider as an easier multiple. Namely, instead of looking at G4, I simply consider G4 prime, which is k bar cubed times G4. This is still a bona fide G4 flux. This is now replying to 2 cycle. In this case, what I would then write down naively as lift is this expression for A prime, which now is in Sharp with integer coefficients. So I work out the corresponding divisors. And so far, so good. The upshot is that the G4 and the G4 prime are proportional to each other. The lifts into chow, the map into the linear, and this map dr are all linear operations. So since G4 and G4 prime are proportional to each other, so must be their resulting divisors. And in proper mathematics terms, what I'm saying here is therefore that dRA, that is the divisor that I'm getting from the flux A, times k bar cubed must be a divisor which is linearly equivalent to the one that I'm getting for A prime. And that is exactly a root bundle constraint. So in also taking the spin into account, I can actually compactly write down all these root bundle constraints in the QSM in this table here. So what I'm doing in the first line is I'm looking for this power of the canonical bundle on this curve. And I'm looking for 2 k bar cubed roots of that. And the factor 2 here is exactly because I'm also including spin in this root bundle constraint here. So there's 2 things to remember here. One is, of course, what I've just done is I've circumvented my ignorance about the intermediate Jacobian. If I knew that, then I would know exactly which lifts exist, and then I would work out from these exactly which root bundles I get. But in general, I cannot expect that all root bundles that I can construct mathematically on the curves are also physical in the sense that they come from an F-theory gauge potential or gauge field. So an interesting but also very challenging question, because it again takes you into looking at the intermediate Jacobian, is to identify exactly which roots are physical. That is something that I reserve for exactly this level of difficulty for future work. And I will today confine myself to do something which is simpler, namely I will look at the necessary condition for F-theory MSSMs within the QSMs. That is, I will look at the curves, I will try to construct root bundles as solutions to the constraints that I've just shown on the previous slide, and I will subject these constraints in addition to a second constraint, namely to have the right number of chiral fields. So in the case of the quark doublet curve, I want on the quark doublet curve H0 to be 3, but H1 to be 0. And at the same time that this root is a solution to this constraint here. So the first thing that I will do is illustrate that that actually has a solution mathematically. And I will at this point even simplify my task by looking at the space with k bar cubed equals 18, where this task simplifies because then it's sufficient to actually solve this root bundle constraint here. Take this one to the power 12, it actually recovers the previous one. So I'll solve this constraint and show that there's a solution with h not equals 3. The second thing that I will do is I will actually extend this to a study over all QSM bases and thereby see if maybe one or the other space is more favorable for the absence of vector-like exotics. So as for proving the existence of a solution to this constraint, the first thing to notice is root bundles on smooth, irreducible genus 1 or genus 2 or larger curves is hard, really hard. So don't do it. On nodal curves, the things are actually well studied and classified by mathematicians, which means essentially it's all well understood, and that's exactly what I'm using here. So instead of working on the smooth physical curve, which I'm denoting in the box on the left, I will take a deformation to a nodal curve, which may or may not be physical. What I'm doing here is to say, first of all, I care that it's mathematically well defined. If it's physical, it's on a different page, so to speak. Then on this nodal curve, I'm actually using this construction by Caporaza, Casagrande, and Canalba to actually construct so-called limit roots on the full blow-up of this nodal curve. This is a line bundle. I define a push forward of that gives me a torsion-free, non-locally free sheaf on this nodal curve, which has the same H0. And then I push that thing back to the original curve along this very deformation that I started with. This will ensure that it recovers a root bundle and solves the root bundle constraint on the smooth curve. Secondly, I know that since I have now 8, 0 being 3 established on that curve, and that matches the chiral index, I can't go any lower with the 8, 0. But also, I'm going from a very special curve, a nodal curve, to a very more generic curve here, which means that by upper semi-continuity, the 8, 0 must not increase neither. So as it can't decrease nor increase, it must remain 3. So I get on PR the existence of a root with 8, 0 equals 3, which is exactly what I want. So by employing this logic, I've actually just simplified my task to actually construct a limit root bundle for you over here in this right box in the full blow up of the curve. And that is what I'm going to do now. I'll do with a little diagram here. This is the dual graph of the nodal curve in the particular geometry that I have in mind. A red bullet here indicates a component of that curve which is genus 0. A red one is a component with genus 1. Any line here indicates a nodal singularity among them. And the degrees that I'm noting, the numbers that I'm noting down here are the degrees of 2 times the canonical bundle on that curve. And our task is to find third roots of that, with, in addition, the property that they have 8, 0 equals 3. So the prescription by Capodasa, Casagrande, and Canalba is to actually turn this into a bi-weighted graph subject to various rules. Namely, I must, if I'm looking for kth roots, then they allow me to take values between 1 and k minus 1. Here I'm looking for third roots, so I take the values to be either 1 or 2. Along each of the lines, I place 2 weights such that their sum is k, so in our case is 3. So I have W1 plus W2 equals 3. Which leaves me with 2 solutions here. Either I take 1, 2 or 2, 1. And secondly, the interpretation of that is that essentially the degrees are shifted here. Namely, if you have this, let's say a red 0, which has a 2 and a 1 next to it, then it means I'm shifting away along one line, a degree 1 contribution, and in the other direction, degree 2 contribution, which reduces the degree on this red curve with 0 by -1, -2 to -3. These shifted degrees are then absorbed by the blow-up P1s, which are placed along these lines, and there we're always getting degree 3. So the result of this shifting of degrees is this diagram here, where I have induced the blue P1s, the blow-up P1s as blue nodes. So that is now an image of the full blow-up of that curve, where the blue ones are exactly replacing each node by a P1, and the lines are now no longer nodal singularities, but just intersection points among the curves. And you see that the degrees have shifted, and I can actually divide each locally by 3. This is the last step that I'm doing. I divide it by 3, and this defines a line bundle on the full blow-up of this curve. Again, once we push this forward to the nodal curve, that defines a solution for this equation here on the nodal curve. So last but not least, I claimed that I actually proved not only existence of these roots, but with 8, 0 being 3, so I better count the sections. And here's what I'm doing. I observe that on the blue exceptional lower P1s, I have a degree 1 line bundle that has 8, 0 equals 2. Also, I have to impose 2 boundary conditions there. This one can show uniquely fixes these sections on the blue P1s. I call these ones therefore bridging sections. No matter what happened on the other components, these bridging sections will actually do the clearing for us. Hence, the 8, 0 on the overall curve is just the sum of the 8 zeros on the components of the nodal curve. So as for those, so what we're looking at is the red -1s, the red 1 here, and the 2 green ones. So the red -1s are again genus 0 curves carrying a degree -1 bundle. This has no sections at all, hence ignore those. And you realize that you're actually only focusing on C1, C3, and C11. That's the reason why I labeled these components in the first place. C3 is a genus 1 curve with a degree 1 bundle, has 1 section. C11 is a genus 0 curve with a degree 1 bundle that has 2 sections. And now C1 is a little bit trickier because it's genus 1 and has degree 0. That is where mathematically Villeneuve jumps can happen. But irrespective of the outcome, I know that there is at least 1, in fact, I know there are at least 8 roots in the case at hand that have no 8, 0 on C1. So I get 0 sections on C1, I get 1 on C3, I get 2 on C11, which is 0 plus 1 plus 2 equals 3 in total. And that completes the argument. So I'll make a brief observation here, namely towards the Higgs curve. Eventually, of course, we want to have H0 equals 4, because that would mean we have exactly one Higgs field there. That would mean that we typically have to think about, can it happen that we jump from some high value to lower value of number of sections as we go from the nodal to the smooth curve? And this is an involved mathematical question, but can be answered in full generality in case I'm looking at a rational curve. And essentially the statement that I have on this slide here says, do the same that I've just done. Then you find the following: there is a jump on this rational curve if and only if you find a non-zero product of an H0 on one component and an H1 on another component. And that somehow looks like a very physical thing. I should say we're still trying to shape in this, bring this into shape and understand it in full generality, but at least the naive understanding looks like the following, namely,
I'll think you've got mostly 5 more minutes.
Okay. So in going to this nodal limit, what you're usually doing is that you're enhancing your gauge symmetry from an SU2, say, to an SU2A times SU2B. These gauge devices intersect. At the intersection, you have bifundamental matter, let's say in 2 bar and 2. And then our nodal curve will typically have components sitting in both of these, each again coming with certain matter localized on it. Let me look at the H0 on 1, which is then fundamental of 2, the trivial of SU2B, and H1 on the other. That would mean I'm looking at a field in trivial representation of SU2A, but anti-fundamental of SU2B. And now looking at these 3 fields, you notice that I actually can combine those into a Yukawa interaction, actually giving me a VAV, or giving a VAV to alpha would then generate a mass term for the pair psi A, psi B bar. Hence, since psi A is an H0 and the psi bar B is an H1, it seems that this mass term is absent if I have that, if both of these fields are absent, or put differently, it is there if both of these are there and there is, let's say, a non-zero web for that one. Somehow this web is not yet seen in this rational case, but this this presence or absence of the psi A and psi B bar is somehow beautifully reflected in the math result that I've just shown you. So that's an outline. That's still work in progress. Let me now go towards this statistical study and extend essentially what I've shown you about these dual graphs and limit linear roots. Namely, if I assume that all my components of these curves are genus 0 or genus 1, just as in the example that I've shown you, then you can actually automate the process. Given a dual graph, you can find all weight assignments on the full blow up, and you can find the H0 of that corresponding limit linear, the limit root. That is something that is implemented in a package called the QSM Explorer, and that is what we use to scan over the various QSM geometries. We focused on a particular subset of these geometries, eventually taking us to look at all spaces with k bar cubed equals 6 and some of the spaces with k bar cubed equals 10. So the crucial observation is that when we first looked into this, it really felt as if this should probably intricately depend on the triangulations, and there are many triangulations, 10 to the 15 in times. So that is the point when I already started to get ready for like a very involved computer scan, possibly with all sorts of statistical applications for machine learning and so on. But eventually turned out that actually there's a bit of a miracle happening here, because these dual graphs more or less count the Picard group over K3 in these 3 folds. And that is work by Batreyev and later Cox and Katz and Kreutzer, which told us that actually these dual graphs and the numbers that we place in them are actually the same for all triangulations. That is a bit of a miracle and came completely unexpected for me, but a very, very nice finding here, which allowed us to, first of all, do these scans of all of these spaces. And the second important observation by my collaborator Miang Liu was that actually we can simplify the task even further. Namely, instead of looking at these involved graphs on the left, we can actually remove tree-like subgraphs, thereby look at a simpler graph, the one on the right in the example at hand. And arguably, you would expect that the combinatorics is a lot simpler on the right one. The crucial observation is that, however, you count the same number of limit roots on the right one and the same 8 zeros. So that simplifies our task even further. So with that all said, we did the scan, and I'm giving you here the results for k bar cubed equals 6 spaces. There are a total of 12 to the 8 roots that you find on the smooth curve. And I'm listing here with this number NP3, the number of limit roots that our computer was actually able to construct and for which we know for certain that they have H0 equals 3. What we notice is that for this polytope delta 8, the largest one in this class, I should say, we're having by an order of magnitude one more limit roots with H0 equals 3 than for the other spaces. So even though our skin is limited, as it only looks for a particular subset of all roots, and we don't fully understand the jumps that happen as we go from the nodal to the smooth curve, with the current techniques, it still seems as if the most promising space for absence of vector-like exotics on the quark doublet curve is any base space that is obtained from triangulations of the delta 8. So with that said, I'm ready to summarize. Namely, I hope I could convey that root bundles appear naturally in the QSMs. And I hope I also gave you a feeling for how we can actually deal with those on nodal curves. Essentially, this image here again summarizes our strategy in that we are taking it to a nodal curve where we can make statements and then take a little bit of deformation theory to get us back to the smooth case, thereby arguing that we can actually find solutions to the root bundle constraints with the cohomologies required for an MSSM. And we can also extend this systematically to all QSM bases, thereby arguing that it seems most likely at this point with the current techniques that if you take a base space obtained from a triangulation of delta 8, then you are in, that seems to be the most likely scenario for having no vector-like exotics. With that said, outlook, of course, our ultimate goal is to come up with an F-theory MSSM construction. That is what I haven't done today, but I hope that these technical advances bring us closer to establishing this one vector-like pair on the Higgs curve. Technical extensions that can be done and which we are looking into as of this speaking to get closer to this goal is to extend our counting to be done on the Higgs curve directly. It's a bit more involved because the curve is more complicated, but in principle possible. Then also extend it beyond these limit linear roots in the full blow up so that we also extend our statistics there. More ambitiously, you could say there's the topology of the dual graph, which might tell you something about how many root bundles you find. Can you find a correlation between the two? The answer of which I don't know. Then there's conceptual questions about the transition from the nodal to the smooth curve, circulating around the jumps, find good conditions for that to happen on genus 1 or larger curves, or even classify the defect of that. And last but not least, and probably the most crucial question here, but also the most challenging one, is to think about these top-down conditions, i.e. which root bands do you really obtain from an F-theory gauge potential. So with that said, thank you very much indeed for your attention.
Let's thank Martin for giving an excellent talk. And if you have any question, please raise your hand. See if there is any question. Okay, can I ask you a question? So let's say you engineer some Higgs field in MSSM in F-theory compactification. Can you compute the Higgs potential like Mexican had or the MSSM version of the Higgs potential? And if you cannot do it right now at this point with the technology you have, which technologies do you need to have it to compute them?
So I think the closest that we are having in this regard is probably I guess explicitly constructing these fields is already very challenging. So I guess constructing any related potential will be very challenging as well. So probably the answer is no for essentially technical reasons. Mm-hmm. So I guess so your question was, why is it technically challenging, right?
Oh yeah, like if you could answer that, that'd be great.
So I guess so again boils down to finding an understanding on this nodal curve and then taking it back to the smooth curve. The smooth curve is where you would physically want to end up with, and I guess the reason why I'm looking in this nodal curve is because I have such a hard time on the smooth one, finding these solutions there, writing down anything for them. Let's say even simpler Yukawa interactions computations is a very tricky thing there. So it's really boils down to having essentially a problem to finding these functions on the smooth curve, and thereby going to the nodal curve and taking it back again to the smooth curve is a tricky thing. We're looking into this at this point, but I think we are still a long way from even talking about any potentials or interaction terms here. At this point, we're really just talking about number of solutions, number of functions. So I guess we are technically very, very far away from this still. Hopefully sometime in the future, but not at this point, I'm afraid.
I see. Thank you so much. Is there any other question? Okay, there is none. Then let's thank Martin again.